Hello, my name is Mingzhu Liu and I am a senior studying computer science in University of Michigan. Our project is titled Survival Analysis on Chest Radiographs with Deep Learning. The motivation behind our project is that chest radiography is a common diagnostic imaging test that helps with clinical risk estimation and triage. In this project, we build models that take chest radiographs as inputs and outputs the probability that the patient survives after some time t. We then compare the performance of the models. Figure 4 shows survival curves. As time from the start of the clinical trial increases, the probability that a patient still survives becomes lower. We assume that the data could be right-censored, which means that we do not know the outcome of some patients. The dataset we are using is a prostate, lung, colorectal, and ovarian cancer screening trial dataset. It contains chest radiographs in grayscale, radiologist impressions or concepts such as COPD, demographic data such as race and sex, time to death, and sensor indicator. Chest radiographs are resized and cropped at random positions. There are 89,643 data points in total, and they are split into training, validation, and test. The first building block of our model is the encoder, which is a convolutional neural network that takes a chest radiograph as input and outputs predicted concepts. We are using DenseNet 1-to-1, pre-trained on other chest X-ray datasets. The second building block is the survival model that takes demographic data and concepts as input and outputs survival probability. The models we are using are Cox proportional hazards, deep survival machines, and binary survival classifier, which is the baseline model. We are using two evaluation metrics, area under the receiver operating characteristic curve and the expected calibration error. The AUC measures how well the outputs are ranked. Models that achieve high AUC gives higher scores to positive samples and lower scores to negative samples. ECE measures how badly calibration is. For a model that achieves low ECE, for example, an output of 0.8 means that it is 80% confident that the sample is positive. We build two models. The first model is called the independent model. We first train an encoder that takes a chest radiograph and outputs concepts. Then we train a survival model that takes the predicted concepts and ground truth demographic data as inputs and outputs a survival probability. The second model is similar to the first one, but the encoder and the survival model are trained jointly. The jointly trained model takes a chest radiograph and demographic data as inputs and directly outputs a survival probability. There are two kinds of jointly trained models, concept bottleneck models and end-to-end models. They are both trained using time-to-death data, but concept bottleneck models are also trained using ground truth concepts. Concept bottleneck models are powerful in that we are able to obtain not only the predicted survival probability, but also the predicted concepts, which might be helpful in explaining how the model decided the survival probability. We compare the results of the models. Binary survival models perform worse than their DSM and CPH counterparts. Joint DSM and CPH model achieve better AUC than their independent counterparts, which means they have better discrimination performance. However, they also achieve higher ECE, which means that they perform worse in terms of calibration. End-to-end models and concept bottleneck models achieve comparable performance. In the end, I would like to thank RIS for supporting me throughout the program.